Hi students, Professor Nugent here. In this video, we're going to continue discussing multiple regression. We'll talk about some more mechanics around multiple regression, and we will conclude with the expected value of OLS estimators. So there's one thing that I'd like to talk about in terms of mechanics and interpretation of the coefficient beta 1 hat. This estimated coefficient, this represents this, we can think about this as the relationship between the dependent variable and the independent variable. So between, for example, y and x1, netting out the effects of the other independent variables, the x2 through xk. If we want to think about a simple example, we can just think about a model with two independent variables, and we have the predicted regression equation here. Y hat is equal to beta naught hat plus beta 1 hat times x1 plus beta 2 hat times x2. And as we just discussed, beta 1 hat represents this relationship between the dependent variable and independent variables, netting out the effects of the other independent variables. So this is the sum from I equals 1 to n of r1i hat times yi all over the sum from I equals 1 to n of r1i hat squared. Where this r1i hat, this is the residual of a regression of x1 and x2, which in effect is the part of x1 that is unrelated to or netted from x2. All right, so you have just the part of x1 that is unrelated to x2 in this R. And so this beta 1 hat, in essence, represents, you're looking at something like the covariance divided by the variance, where this is only the part of x1 that's unrelated to x2. All right, so that's how we can interpret this beta 1 hat. Now what I'd like to do next is look at the relationship between simple regression and multiple regression in the case that multiple regression is the population model. So let's write down two regressions. I'm going to write down y tilde is equal to beta naught tilde plus beta 1 tilde x1, and then y hat is equal to beta hat plus beta 1 hat x1 plus beta 2 hat x2. All right, so assume that our hats are the unbiased estimates. Then beta 1 tilde, so if we decide or for some reason end up running the simple regression instead of the multivariate regression, then we're going to have an estimate beta 1 tilde, which is going to be equal to beta 1 hat plus beta 2 hat times delta 1 hat, where delta 1 hat, this is the coefficient from a regression of x2 and x1. So what does this show us? If we leave out this variable, x2, in the simple regression, and x2 is related to x1, then our coefficient, beta 1 tilde, is going to contain the effects of both x1 and x2 together. The only time that beta 1 hat will equal to beta 1 tilde is when beta 2 hat is equal to 0 or delta 1 hat is equal to 0. If beta 2 hat is equal to 0, then x2 does not enter the population regression, and so x2 would not be contained in the residual. So there would be no reason to bring that into the regression equation, and we wouldn't be suffering from omitted variable bias. If delta 1 hat is equal to 0, then x1 and x2 are not correlated, and there would not be that concern for omitted variable bias, and we would still be able to make our ceteris paribus conclusions. These are the only cases that beta 1 hat is going to be equal to beta 1 tilde. And once we prove that beta 1 hat is, or write down that beta 1 hat is our unbiased estimator, we're going to show what happens when we have this bias going on. So let's think about what assumptions do we need to make for our linear regression model now that we have multiple variables. What assumptions do we need to write down for this model to work? So we're going to get that at the expected value of the OLS estimators for the multiple regression model. What we're doing is deriving statistical properties of the estimator when random sampling is done repeatedly, all right? And the expected value that we're going to discuss is conditional on 4 assumptions. We need 4 assumptions. The first is that the population or true model is linear in parameters. I'll recall that we can have nonlinear functions of the data where we have log transform data, we can have interactions, we can have polynomials in the data, but we must have a model that's linear in the parameters. The second assumption is that we have a random sample of n observations. On, let's see, yi, we're going to start with x1i, x2i through xki and yi for I equals 1 through n. That's our random sample. Next, we need to be able to assume no perfect collinearity. What do we mean by no perfect collinearity? So we're saying that none of the independent variables are constant. So we're saying that x1 does not have the same value for all observations I equals 1 through n. And there are no exact linear relationships between any of the x1, x2 through xk. Now, there's typically, perfect collinearity typically happens because of an error, such as including one variable in thousands of dollars and one variable in millions of dollars. But this is an assumption that is easy to satisfy by dropping the variable that is perfectly linearly correlated with whatever other independent variable of interest has been included in the equation. And finally, we need the 0 conditional mean of u. So that the expected value of u given x1 through xk is equal to 0. And this fails in the case of omitted variable bias. If we have no omitted variable bias, then our independent variables x1 through xk are plausibly exogenous. If we're suffering from omitted variable bias, if our independent variables are related to the stuff contained in U, so otherwise we have endogeneity going on, which is a problem that we're going to discuss how to solve in later chapters if we are unable to simply bring those variables out of the error term and into the equation. So if we are able to satisfy all of these assumptions, then OLS is unbiased, okay? OLS is unbiased, and the expected value of beta j hat is equal to beta j for j equal to 1 through k. All right, the estimator is unbiased. It's not really correct to say that an estimate is unbiased, but the estimator, the estimator of beta j hat, this is unbiased. So in repeated samples, you expect on average that this estimate will be equal to the true population parameter. And the proof of this follows from the work that we did with the simple regression model. Thank you.